Hello. Mm, Good evening, everyone. I hope I'm audible. Can someone confirm? Am I audible? Hello. Uh, am I audible? Hello. I hope I'm audible. So I'll start with the fourth live session of the NPTEL course, Basic Principles and Calculations in Chemical Engineering, course instructed by Professor S.K. Majumder from IIT Guwahati, and myself, Chaitra Borkar, a Ph.D. scholar from IIT Delhi, who will be conducting this session. So some information about these live sessions is that these sessions will be conducted every week on Tuesday from 7 to 9 p.m. for the duration of this course. The recordings of these live sessions has been made available to you. The links have been shared with you, and you can also access it through my YouTube channel. The structure of these sessions will be that firstly go through the overview of the lectures for the corresponding week, which is the fourth week this time, and then solve some sample problems related to your assignment questions. So the overview of the lecture 11 was that it dealt with the state equation of ideal gas and calculations. So firstly, we discussed the ideal gas equation. So ideal gas equation. So basically, ideal gas equation is the combination of these laws which were propounded by different scientists. So Boyle's law gives us the relation of P versus V for a constant temperature. The Charles law gives us the constant temperature and a fixed amount of the gas. Then Charles law gives us the relation between the volume and temperature for a fixed pressure and the fixed amount of gas. Same goes for the Gay-Lussac law, which gives us the relation between pressure and temperature for fixed volume and fixed amount of gas. So if we combine all these laws, it gives us the ideal gas equation, which gives us the relation between PV and T. So this is and the number of moles. So if the number of moles are constant and the ideal gas and the universal gas constant is also there. So if we consider this term as constant, so we get P1 V1 by T1 is equal to P1 P2 V2 by T2. Um, Next, we studied the Dalton's law. So Dalton's law tells us that the summation of the partial pressure of all the constituent gases of a mixture gives us the total pressure, which is illustrated using this schematic. So if we add all these partial pressure, we get the total pressure of the air. All these are the constituents of the air. So oxygen, nitrogen, argon, water vapor, carbon dioxide. And same goes for the Amagat's law. So the partial volumes, the summation of that of all the gas constituents in a mixture gives us the total volume. The 12th lecture dealt with the state equation of non-ideal gas and calculation. So basically, we'll first know what is an ideal gas. So what is the ideal gas behavior? What is meant by the ideal gas behavior? So ideal gas has two characteristics basically. So it has particles of point size, basically negligible volume or zero volume. The particles have negligible volume and no interparticle interaction. So these are the characteristics of ideal gas. So if we want to study non-ideal gas are basically real gas. These particles have volume because we know real gases have some volume. The particles of the real gas have some volume. The energy is lost in collisions, and there are intermolecular forces present. As opposed to the ideal gas, where the particles have no volume, collisions are elastic, and no interactions between the particles take place. And this statement here, real gases behave like ideal gas at high temperature and low pressure. How this comes about is that suppose This is a container, and there are particles of some gas, and it is at very low pressure. So at low pressure, the particles may be considered to be far apart, so that the interactions, interparticle interactions may be insignificant. And also at high temperatures, what happens is that the particles are imparted so much of kinetic energy because of the temperature, because of the higher temperatures, that the interparticle attractions may be neglected. So the ideal gas behavior can be observed at high temperatures and low pressures. So that means that the ideal gas behavior may not be present at high pressure and low temperature. All right. So firstly, we dealt with the non-ideal or real gas. Then we discussed the difference between the ideal and non-ideal gas. Then we talked about the generalized equation of state for non-ideal gas. So here we introduce a factor called compressibility factor. So for the generalized equation for non-ideal gases, PV is equal to Z N R T, which gives us the deviation. This compressibility factor gives us the deviation from the ideal behavior. So these are the this is the plot of the compressibility factor versus pressure. So we see that at higher pressure there is a very large deviation from the ideal behavior. So ideal gas have a compressibility factor equal to 1. So at higher pressure we see that many gases deviate drastically from the ideal gas behavior. Next, we studied about the critical temperature and pressure. So critical temperature, basically, if you see the phase diagram here, P versus T of a substance. So these are the different phases which we get. It has vapor phase, liquid phase, solid phase, and these curves represent the equilibrium curves. So this will be vapor solid curve. This will be the vapor liquid curve. This will be the liquid solid curve. Equilibrium curves. And then beyond this T critical or the critical temperature, even if we want to, even if we increase the pressure, the gas will not liquefy. In this region, if we see any temperature in this region, if we increase the pressure, the vapor will get changed to liquid. The pressure is increasing in this direction, so if we increase the pressure, the vapor changes to liquid. However, when we go beyond this temperature T critical, even if we increase the pressure, the vapor or gas will not be liquefied. So this is the critical temperature, and the pressure at this critical point is critical pressure. Then we studied about the other equations of state such as Viral equation, van der Waal equation, Penn-Robinson equation, Redlich-Kwong equations, and Serve-Redlich-Kwong equation. So the van der Waal equation is given by this relation. So here this term is added to the pressure and this term is removed from the volume. So this accounts for intermolecular interaction, and this basically gives us the volume correction, because as the real gases do not have particles which are point size, they have some significant volume. That's why these volume corrections are made. So this is another form of writing the van der Waal equation, where this small v is basically molar volume. So small v is equal to capital V by number of moles. And these constants, van der Waal constants A and B, are given using these relations, which tells us that they depend on the critical temperature and critical pressure. Next, we studied the K mixing rule for non-ideal gas mixture. So how to calculate firstly the critical temperature of a mixture, critical pressure of a mixture, and then compressibility factor of the mixture. So now let's start with the solving the sample problems related to your assignment 4. So first question, which one of the following values is the universal gas constant? So, can anybody give me the answer for this? Anybody present? What would be the correct answer here? So, firstly, look at the units. So, PV is equal to nRT. So, suppose there is 1 mole of gas, ideal gas, and we know we want to calculate the value of universal gas constant in these units, liter atm by mole Kelvin. So at standard temperature and pressure, so pressure will be 101,325 Pascal, but you want it in atmospheric, so 1 atm. And volume will be, volume at standard temperature and pressure of an ideal gas is 22.4 liter. Okay, so 1 into 22.4 upon, if we take this n below, n is 1 mole and T is 273.15. If we calculate that, so 22.4 by 273.15. It comes out to be 0.08206. Or if we take a much more exact value, 222.415. So this comes out to be 0.08206 liter atm by mole Kelvin. You see how these units came about? So basically, standard pressure is 101,325 Pascal or 1 atm. The standard volume of gas, volume of ideal gas occupied at standard temperature and pressure is 22.415 liter. So P, V, N, and T gives us R. So the correct answer here is D option. All right. So we go move on to the next question. What would be the SI unit of universal gas constant? We need to choose the correct answer here. What will be the correct answer here? Can anybody give me the answer? The SI unit.
B.
B. Are you sure? SI unit. I'm talking about SI unit. So let's see what will be the unit, general unit for a universal gas constant. So PV by NT basically. So P has Pascal unit, SI unit. V will have meter cube, SI units I'm talking about. N will have mole and T will have Kelvin. So it will be Pascal meter cube by mole Kelvin. So Pascal meter cube, if you see, Pascal is Newton per meter square and into meter cube. So this get cancelled, so it becomes Newton meter, which can also be written as joule. So joule per mole, sorry, joule per mole Kelvin. All right. So the correct answer here is C option, joule per mole Kelvin. Next question. Volume occupied by an ideal gas at STP is, I have already told you this. What would be the correct answer here? The volume occupied by an ideal gas at STP is, okay, so we can all do not write in the text box, do not write in the chat box. You can give me the answer, unmute yourself and give the answer.
B.
Yes, correct. B is the correct answer here. So we can also compute that value. So STP is 273.15 Kelvin and pressure is, sorry, 101325 pascals. All right. So we can compute the volume from here. So PV is equal to nRT, or we can write it as 1 atm. So 1 atm into V into N is 1 mole we take, R we take as liter atm value, liter atm per mole Kelvin value, 0.08206 into T is 273.15 again. So we can calculate the volume from here, 0.08206 into 273.15. So this comes out to be 22.415 around liters. All right. The correct answer here is 22.4 roughly. Next question. For 1 mole of an ideal gas at a constant temperature, the relation between volume and pressure will be, what will be the correct answer here?
A answer.
Yes, correct. Because if we look at the relation PV, ideal gas relation, P is equal to nRT. If this becomes, sorry, not this, sorry. PV is equal to nRT. So this is constant here. This is also a constant. This is also a constant. So PV is equal to constant. So basically, P is 1 by V. So this is the correct answer. P is inversely proportional to volume. Next question. The gas having a pressure of 5 bar is heated from 0 degree Celsius to 546 degree Celsius, which is then consecutively compressed to 1/3 of its original volume. The final pressure value is, so suppose there is a system which has P1, V1 and T1, and another, and the system after some time changes to another state, P2, V2 and T2. So we know P1 as 5 bar. All right. We know the initial temperature as well, T1, which is 0 degree Celsius or 273.15 Kelvin. Then we know, we do not know V1, so we'll write it as V1. And then we don't know the P2. P2 we don't know. V2 is given by this relation. So V2 is 1/3 of the initial value. So V1 by 3. And we know the final temperature T2 is 546 degrees Celsius. So we add 273.15. So 819.15 Kelvin. All right. So we can equate these two states. P1 V1 by T1 is equal to P2 V2 by T2. So using the ideal gas relation. So P1 is 5 bar, V1 we do not know, V1. Then T1 is 273.15 is equal to P2 we do not know, V2 is related to V1, so V1 by 3 into upon 819.15. So if we solve this for V1, V1 will get cancelled. If we solve this for P2, it becomes P2 is equal to 5. This 3 goes up. This 819.15 also goes up. And denominator has 273.15. So this P2 becomes 5 into 315 into 819.15, big number, divided by 273.15. It gives us roughly 44.98 bar. So roughly 45 bar, because the unit of pressure here was bar. So the correct answer here is the C option. Next question. At what temperature will 0.6 moles of argon gas occupy 12 liters at 2 atmospheric pressure? So here we can calculate, we need to calculate the temperature. We know the ideal gas relation, PV is equal to nRT. So we know the units liter ATM. So we also know ideal gas or the universal gas constant in the those particular unit as well. So the pressure is 2, volume is 12 liter, N is 0.6 moles, R we know 0.08206 in this particular unit. The unit needs to be consistent, and T we do not know. So we can compute the temperature from here. So 2 into 12 is 24, divided by 0.6, 40, divided by 0.08206. So it comes out to be 487.45 Kelvin. So the correct answer here is D part, 487.45. Next question. 60 gram of a gas occupies 40 liter at 650 mmHg and 25 degrees Celsius. What is its molecular weight? So we need to compute molecular weight. We know the given weight. So basically we firstly need to find out number of moles. So from there we can find out what will be the molecular weight, because N will be is equal to given weight upon capital M, which is the molecular weight. So we are given pressure, volume, and temperature as well. So we can compute the number of moles. So firstly, the volume is 40 liter. Pressure is given in mm of Hg. So firstly, we need to convert it to atmospheric. So 1 atmospheric is equal to 760 mm Hg. So 650 mm Hg will be equal to 650 by 760 atmospheric. So that will come out to be 0.855 atmospheric. So 0.855 atmospheric. So we know volume, we know pressure, we know temperature. 25 degrees Celsius is 298.15 Kelvin. So keep the unit consistent. Don't take directly degrees Celsius temperature, as the R, or the universal gas constant, is 0.08206 liter atm by mole Kelvin. So keep the unit consistent always. So PV is equal to nRT. So N will be PV by RT. So 0.855 into what are the liters? 40 liters upon R is 0.08206 into temperature is 298.15. So number of moles will be 1.3978 moles or 1.398 moles. So given weight we know what will be the molecular weight. Molecular weight will be given weight by number of moles. So given weight is 60 gram, number of mole is 1.398 moles. So 60 by 1.398. So 42.91 or 42.92. So roughly 42.91 we can say the correct answer, gram per mole. So the correct answer here is B part, 42.91 gram per mole. Eighth question. As per Amagat's law, the summation of partial volumes of ideal gases in a mixture is equal to. What is the correct answer here? The correct answer here is the A part. So we have seen that VI summation of it is equal to VT. So this gives us the summation of the partial volumes of ideal gases in a mixture equal to total volume. Next question. 30 mole of O2 is mixed with 120 mole of N2, nitrogen, at standard ambient temperature and pressure. The temperature is 298.15, ambient temperature and pressure 298.15 Kelvin, and pressure is 10 to power 5 Pascal. Calculate the total volume of the mixture as per Amagat's law. So total volume of mixture. So Vt will be is equal to VO2 plus Vn2. So we can compute VO2 because we know the PT and PT and N. So we can calculate the VO2. So VO2 will be P is 10 to power 5 Pascal. Then, sorry, not that. Moles are given. So 30 mole into 8.314 joule per mole Kelvin, joule per mole per Kelvin, and into temperature is 298.15 upon 10 to power 5. And Vn2 is 120 into 8.314 into 298.15 into 10 to power 5. You can see this term here is common for both. So basically you could also add these 30 plus 120. So 150 into the total moles of mixture, and you could have multiplied with this factor also. You can do that as well, and you can add the volume individually as well. So volume of O2 is 30 into 8.314 into 298.15 divided by 10 to power 5. So 0.7436 meter cube. Please keep in mind the volume will be meter cube. The unit of volume will be in meter cube. And this will be 120 into 8.314 into 298.15 divided by 10 to power 5, 2.974 meter cube. So VO2 plus VN2 gives us VT. So that will be 3.718. So the correct answer here is D option. Next question. Ideal gas behavior is defined by particles having significant volume and no interparticle interaction, particles having zero volume and no interparticle interaction, particles having significant volume and interparticle interactions, particles having zero volume and significant particle interactions, interparticle interactions. So what is the correct answer here? Ideal gas behavior is defined by what option? Can somebody give me the answer here? We have discussed this just now.
Answer A.
No, B. The,
Okay.
the correct answer is B here. Particles having zero volume and no interparticular interaction. Let me go back. So ideal gas, you can see here, particles have no volume and no interparticle interaction. This is the ideal gas behavior. So these are basically point size particles with insignificant volume. So the correct answer will be B. They do not have any significant volume. The correct answer is B here. Next question. When does the ideal gas equation fail? We have just discussed this. So ideal gas equation follows when there are low pressure and high temperature. So when does it fail? When would it fail? It would fail at higher pressure. So one of these options, higher pressure and lower temperature. Why would it fail? Because suppose this is some container and this has some particles of a gas in it. And if we push the piston, suppose there's a piston above, and if we push that piston way below, so the pressure is increased. It is at a higher pressure condition. And at this point, the interparticle interactions will become significant. Also, at low temperatures, there is not enough kinetic energy to overcome the interparticle interaction. So, interparticle interaction do come into play at lower temperature and higher pressure. So, ideal gas behavior fails there. Ideal gas equation doesn't apply. So, the correct option here is C option, lower temperature and higher pressure. Next question. Beyond the critical temperature, a gas can be liquefied, cannot be liquefied, can be solidified, or none of the above. What will be the correct answer here? Can somebody give me the answer for this?
Can be solidified.
No, cannot be liquefied. There is no relation for the critical temperature for gas and solid. Gas and solid behavior is for, let me show you the phase diagram once more. So if you look at this, you look at this phase diagram. So this is the vapor phase and this is the solid phase. So solid and vapor phase, the equilibrium curve is this. So for vapor to become solid, you can decrease the temperature, all right, or you can increase the temperature, or you can increase the pressure from this point, all right. But here, beyond the critical temperature, there is no relation between the gases and solid phase because this is the supercritical phase. So here, beyond the critical temperature, a gas phase or a gas cannot be liquefied. All right? Do you get it?
Yes.
Even if you increase the pressure, it will not liquefy. Next question. Ideal gas behavior is observed at, so we have discussed this just now. Ideal gas behavior is observed at
Lower pressure, higher temperature.
lower pressure and,
Higher temperature.
yes, correct, A option. So I've given you the explanation that at higher temperatures, the intermolecular attractions are insignificant. Also, the same goes for the lower pressure. So, correct answer is higher temperature and lower pressure. Next question, match the following. So we need to match the name with the name of the equation with the expression. So for ideal gas equation, what will be the correct answer here? It will be matched with the third.
B answer.
Huh?
Answer B.
No, no. Ideal gas equation will be third. PV is equal to nRT.
Huh. Overall B. Yes.
So A is 3, right? What will be the correct expression for the virial equation?
1.
Yes. So from here we see that the virial equation expression. So this is the compressibility factor equating to 1 plus. These are the virial coefficients. So this will be the second virial coefficient. This will be the third virial coefficient. This will be the fourth and so on. So basically it's a series, exponential series. And upon these are the molar volumes. And these viral coefficients are functions of temperature. Please keep that in mind. And these are molar volume. So function of exponential function of uh, uh, the molar volume is increasing in the power with every constant. So this is basically a power series. And then in terms of the molar volume, and these viral coefficients are function of temperature. Next, van der Waal equation. So this only option remaining is second. So this is the van der Waal equation expression. So it will be A3 B1 C2. A3 B1 C2 B part. Yeah. Okay. Next question. In van der Waals equation, the unit of constant A. So we'll write the van der Waal equation first. P plus A by V square into V by V minus B, sorry, is equal to RT. There is no N here because I have taken this as molar volume. This is molar volume, which is equal to capital V or volume by N. So what will be the unit of A constant, the van der Waals constant for intermolecular interaction? What will be the unit of this? Can somebody give me the answer for this? So if you want to calculate the unit, so same unit quantities can only be added. So basically, unit of P will be is equal to unit of A by V square. All right. Only the same unit quantities can be added. Only the quantities with same unit can be added. So unit of P can be or pressure can be Pascal. So that would be equated to A by V square. So and unit of V will be meter cube per mole or meter cube per mole का whole square. So Pascal into meter 6 by mole square will be unit of A. So meter 6 Pascal by mole square. So the correct answer here will be C option. Oh, not true. Not not the answer here. Meter 6 Pascal by mole square. Next question. In van der Waals equation, the unit of constant B is, so again we can do that. So again, the quantities of same unit can be added. So this has this is molar volume, so equal to meter cube per mole. So this will also have the unit as meter cube per mole. So the correct option is B part, meter cube per mole. Next question. What is the unit of the third virial coefficient? So we'll write the virial equation again. G Z is equal to 1 plus Bt by nu plus Ct by nu square plus dt by nu cube and so on. So this is the first coefficient, second coefficient, third coefficient. So we need to compute the unit of this. Compressibility factor is unitless because PV by RT. So this will have the same unit as this. So nu square is meter cube per mole whole square. So meter 6 by mole square. So the correct answer here is B part. Next question. If all the virial coefficients become equal to 1, then it reduces to ideal gas equation. Is this true or false? What will be the correct answer here? If all the coefficients of viral equation, so these are the coefficients of viral equation, if they become 1, will it be equal to the ideal gas equation? No, because then these they need to be reduced to zero to for it to become ideal gas equation. All right. So it will be false because if even if they become one, these molar volumes will still have some significant values, and this will not be equal to ideal gas equation. So it is false. Next question. The expression for compressibility factor is, what is the expression for compressibility factor? We have discussed this. It is PV by nRT.
C.
Yeah, C option. Correct. Next question. The expression for critical pressure, where PR is reduced pressure and P is given pressure is. So, what will be the expression for critical pressure? So, we know reduced pressure is P by
A.
PC, right? And then PC will be P by PR. So, the correct option here is A part, P by PR. So, any questions, anybody? If there are no questions, I'll go ahead and close the session for today.
Where I get the PPT, ma'am?
Could you repeat your question?
Where I get the PPT?
PPT, my PPT?
Yes, ma'am.
Um, I have shared the link with you, the Google Drive link. It has been shared with you. You can go to the your NPTEL course page. You can see, uh, you can also access the video recordings, previous session video recordings, as well as my notes from there. There is a Google Drive link that has been shared there. All right?
Okay, ma'am. Thank you. Okay,
Okay.
thank you.
Yeah, thank you. If there are no further doubts, I'll close the session for today. Thank you, everybody, for joining.